Yes, thank you. We will start because our program is pretty tight and we don't want to waste opportunity to share information with you, since we are anyway starting with more general parts, and some of you may have heard it already. We expect that in the meantime some more people may arrive from the plenary session. The program has been showed outside, but I will just repeat that we are now going to introduce in more detail selected parts of the model code, and we have chosen the one that are about material innovation, assessment, and seismic parts. Steve Foster will give a ground opening, then I will summarize again the total of the content, and we will follow with the presentations. Yes, Steve?
Thanks, Agnieszka. All right, okay, so just to get us started, just got a few thoughts. And I'm just looking at the audience here on who I haven't shown this to before, so we know we've got a big job to do, right? We're already at 1.1 degrees of warming, in fact more. Over the land surfaces, we are at
almost 1.6 degrees of warming. So I mean, the fact that the oceans are at 0.88 means the average comes down about 1.1 degrees. Above the 1850 to 1900 levels. We need to develop climate-resistant infrastructure. We've heard that this morning, heard the interesting team of the Minister talking about this, and the question is how can FIB assist in this? And that's a lot about what the new Bulk Code is about. If we look where we're at, this is a diagram that's taken out of the watching the thread report in the IPCC, and one of the things I find interesting here is that on this report, of course, oil, land use change, forestry, gas and so on, concrete is the only building material that only has a footprint in that space. And that's because of the pure volume of the concrete that we use. It's got nothing to do with the, in fact, concrete is not a high carbon material, right? It's about 300 kilograms for its paint, steel, masonry, aluminium, silica, much higher than concrete. When thinking about this, we're ranking up soil and soil production. It's ranking up silica. Silica production produces 2.5 to 5 indicating for the chunk of so concrete, cement, yes, concrete is not a high carbon material. But this is what we've got left. And without going through the numbers, this is what we've put in the atmosphere already. This is what we have got left for 1.5 degrees, and this is what we've got left for 2 degrees. 1.5 degrees is, I think, in mine energies, is just not unworkable. Again, you saw that number of 4%. That's 4% based on all those that make up about 75 or 70% emissions. But this is the numbers here. Cement process emissions, so they're the ones that tons of coal. That's 2.6% of that floor. And many of my colleagues here will know I present this routinely. We had back to this day, we no longer leave aside it's between 5 and 9 or 6 or 8 or 10, whatever the number. We have active data. It is specified in by the IPCC. And this is the report, Robbie Andrew data, it's updated every year on the work, and we have numbers. These are 2019 numbers, but the reality is the 2024, 2.9, this doesn't satisfy very much. For decomposition of carbonates, it's 1.6 gigatons. The energy is 1 gigatons. The total emissions of carbon dioxide is 6%. Not 10, it's 10. The carbon dioxide is only one of greenhouse gases. If you start to look at greenhouse gas equivalencies, it's what the terminology is and something that is used by my colleagues. And when you look at that, we use 59 gigatons of CO2 equivalent. We add in methane, nitrous oxides, and a whole lot of other gases. and the 2.6%, the 2.6 gigatons total represents 4.4%. So the 4.4% of emissions, 2.6% of which are process emissions, they're the hardest part. So we've got a big job, but we don't need to exaggerate it. So the FIB, Kuya and Yeshka, primarily and others, have been putting together our roadmap to how we can support our national member groups in developing the roadmap to 2050. This will be put online, published fairly soon, but I'm not going to go into any great depth in here, but just to be aware of it, and looking at the different use stages, the different time stages, so product use stages, and end-of-life stages, and how each of these need to be ramped down, and how we can assist them, our members assist in achieving this. And this one here just goes to the longevity and durability. If we continue as we are, we go through a period of time, we intervene, go through a period of time, we intervene. Each of these produce carbon emissions, or we can go through more durable technologies with less intervention over time and save carbon. So different ways. Last two slides. Firstly, we have many areas in our portfolio we need to use all of them. Substitution, we can talk about that a lot. The people to last couple of days, many cases looking at late carbon concrete. Concrete is used for material, we utilise it in structure. It's one area. Reuse. So let's stop pulling down buildings. It's a good start. Sequestration, we do an awful lot. Concentrate on one form, and that's carbon capture. But we have terrestrial sequestration, we have industrial sequestration, and the like. And we need to, I think, particularly on terrestrial. Carbon capture storage, we talked about, and then dematerialisation, and I'll come back later. So just on the sequestration, if I've got $1 to invest, I want to make sure I use that dollar wisely. The best way I can use that dollar. If I look at our industries and I want to bury that into the ground, that's one way I can use that dollar. One of the problems with that is the geological survey needs to be consistent with what the extent's doing. And that's like with gas, so it might be with the whole works and never have it. And we'll have a tank or a good posture nearby and store it. But most cement manufactured that are not co-located on the best geological stratigraphy. That's not what decide where we locate the cement plants. So do carbon capture storage, or yes, we have to capture, it's for English cost. But we can do it other ways. So this is actually a group of researchers at UNSW that work in this wetland upgrade. Basically, the wetland upgrading can take that dot. I don't need to co-locate that plant. Or we talk about good solid principles. I can install whole wetlands up and down the New South Wales coast, which is degraded, and had a whole lot of subsequent benefits. So I think that's all I wanted to say for today. And yes, I know we've got a lot more on the program than this, but this is just one of the big motivators of the model code.
Thank you, Steve. And that is the opening that should make you aware about the ambition that we had with the model code drafting. We want to facilitate all the solution that Steve was showing in the previous slide, from substitution to dematerialization. As I was just saying, the model code is an initiative that is intended to allow engineers to mainstream the innovation. Basically, model code is an operational code. Of course, it's intended to be used worldwide to write the national or regional provisions, but actually you could use it. It has also quite other feature. It is also full of explanations for those who haven't ever opened the book. It's actually built in two columns. One column is provisions, another one are background information, and it connects through to another background documentation. So It is also intended to be a kind of document that explains the certain choices and provides more background information, therefore inspires research, because we need a lot, and education. Well, we took that step of moving from Model Code 2010 to Model Code Edition 2020 with the intention of including what has been generated over the period of these years, but we had already very solid foundation because Model Code 2010 had already introduced sustainability as overarching framework. So we were already at that time a kind of forward-looking in our aspiration. But now, some years later, we were able to go into details of this provision and explain better how to do it. And of course, a lot have happened in terms of innovation. So while our objectives didn't change, we were we even put more attention to make sure that we recognize the context of the worldwide association. Well, sustainability issues, environmental impact is not the only regional problem. Solutions are being developed all over the world, and one of the ambition of us is also to bring it together and share it and interchange and inspire. So that's why this is truly a joint effort, because we need that knowledge and we need that practice and we need that validation in the practice from our approaches. Well, this one I have already shown. You see that it really works like an inspiration for the code, in particular in the context of Eurocode 2. Steve Denton was also showing in his presentation how these two developments are cross-connected. And again, you all know that sustainability is more than only environmental impact. Sustainability is paying attention that we make decisions that are both viable, bearable, and equitable, means that we can pay for it. The sustainability does not, while saving environment, doesn't harm society. And so it means that actually we request from the engineers far more than we used to do. It's not only about structural design, but it's also about considering life cycle impacts, life cycle costs, and balancing these objectives that may often be conflicting with each other. That's also a part of the content of the module code. We will not be talking about that in more detail today, but be aware that there is also an insight into how to take this kind of balanced decisions, and we also work more in that direction. Now, what was one of the very important reasons for update the model code was also the conclusion that materials are being developed in a very high speed. And soon in more detailed presentation, Harald Müller will help you to understand what was achievable and what are still more research is needed category. But again, material concrete has evolved a lot. Its use in practice has evolved a lot, so a lot has been taken from the research to practice and how to facilitate that. Our aspiration was to cover new types of materials, and today, later on, you will hear a story about design of concrete mixes and how we can improve that. Use of ultra-high performance concrete, fiber reinforced concrete. That's only about concrete. We also have a new reinforcing materials. We will also go in more detail into this one. Life cycle perspective. I found it so important, and especially after listening today in the morning to the opening speech of the Minister of Building and Construction. Let's send that message. It's not only about savings during the construction and production. It's also about management of the structures that allow us to benefit from the fact that they are existing, use them in the optimal way, limit the emissions during use of structures, and don't forget that interventions not only have a direct impact by using materials and construction power, but also very high indirect impact. That is also environmental indirect impact, especially when we cause hinder to transport and traffic and with all the consequences of it. So life cycle perspective. But life cycle perspective is also something more. It means that design should consider life cycle as in one of the objectives. So emphasis in the model code, is therefore also on conceptual design phase, because that's when we make certain choices. Also, how to consider and allow for low maintenance structures, or eventually how to plan this maintenance, because this will be needed. Performance-based approach. Well, we are not following Hammurabi in saying that the designer should pay with a very high price for his mistakes, but we look at performance requirements, and performance requirements are not only structural performance requirements, these are also environmental performance requirements, requirements with regard to circularity, requirements with regard to life cycle costs for the structure. For each of them, objectives should be defined, methods must be available, and we provide number of these methods. Obviously, we concentrate on verification of structural performance, but there are also approaches described how to handle validation of verification of other aspects of performance. Well, I think it's a kind of repetition. Again, verification can be done by different approaches. Verification by models is what engineers usually do, but verification by models can be also supported by testing, monitoring, and active gathering of information. And again, later today, you will hear a presentation regarding the use of monitoring and testing as support for the verification. But for some aspects of performance, we need to rely on validation, and that's also very important that we do actually control which level of performance we have been achieving, for instance, for environmental performance. Otherwise, it's all only on paper. Well, example of the presentation in the morning where really the as-built balance has been made of the environmental impact generated allows us also to improve our best practices. Well, this slide far too complicated to explain today, but it's just a reminder that once we start from the high-level objectives, we transfer them into the performance requirements for all these three pillars of sustainability. We need to communicate with everybody within the chain of parties, expertise involved in order to allow the optimal solution. So communication between material producers about what is feasible and what could deliver that performance is necessary. Communication with the designers, but also designers with the construction experts who can improve parts of the design, providing additional improvements, for instance, with regard to detailing of reinforcement, couplings versus overlapping of rebars. Very practical things, but can really have a huge impact on improving our designs. And again, when I say design, actually I should say design, assessment, and life cycle management of structures. Sorry, I'm also an old school. That's what we learned, structural engineers design. Well, we do much more than that. And this is the lower part of this diagram. While we enter the stage of treatment of existing structure, very important is to have the sound approach to assessment of the current safety and serviceability of these structures. Here in the model code, we put a lot of effort to provide models that are actually quite seldom available in the codes around the world. Eurocode only now introduced the chapter on assessment of existing structures. In the model code, you will find provisions for assessment of structures that have corrosion, alkali silica damage, and freeze-throw damage. And again, this is very relevant because the structures have that issues, and we must know how that sometimes material-related degradation, sometimes other aspects of degradation do affect actual capacity and safety. Well, once the decision needs to be taken about interventions, you will also find information about how to do that, how to decide about interventions, how to connect gathering of information to decision-making, how to optimize interval of making inspections to achieve interventions, and how on the basis of that determine the moment of intervention and which technologies are available. Of course, in the model code, not everything is included. Therefore, we have the supporting bulletins in that context of intervention, I will mention Bulletin 102 and 103, which provide the detailed information regarding particular techniques for strengthening, upgrading, and retrofitting of structures, both structural and non-structural. This is also, let's say, like the surrounding of the model code, the foundation of on which model code has been built. No explanation to the slide, but only a message. Structures, new and existing, it's a continuum. Therefore, we look at FIB at the safety philosophy's basis from the same principle, risk-based approach. We accept certain risks for certain reasons. How we handle that in our verifications, partial factors, global factors, and other approaches as a consequence of this consideration that have been made upfront. Risks are something that we have to handle, and observation that have been made is that the costs of minimizing these risks for existing structures are higher than for new structures. Therefore, from the economic perspective, it's desired and optimal to have a diversification in the target reliabilities for new and for existing structures, which again translates it in different values for the partial factors of global factors of safety in both cases. As I say, all these formats are available. Usually we will use the mid part of it, but know that there are also situations in which we can rely on reliability-based assessment, in particular for exceptional structures, in particular for assessment of critical structures, and we also have information on that, down to deemed to satisfied rules that of course need to be properly calibrated and connected to make sure that when we follow deemed to satisfied, we actually meet the same safety level that we aim to. Level of approximation, it may happen that you will hear more about it during the presentations today, because for the models we provide a suite of models at different levels of approximation, which again come with different effort in conducting that verifications, but by improving the accuracy, we gain often in the sense that we prove that some interventions would be unnecessary, so it pays back. Well, more refinement in modeling comes with the requirement, and one of these requirements is availability of information. Very many of these methods will require better and more detailed inspection of our structure so that we can have that. So there is always the balancing of the effort, the costs, and the benefits. But well, the choice is to the designer, because the choice is obviously case specific. And what this level of approximations have in common, or what that differentiates them from each other, is the fact that generally speaking, the more refined levels of approximation consider certain mechanisms that have not been accounted for at the lower level of approximation. So simplification leads to more conservative assessment. More refined model leads to more exact assessment and benefits of it. Deterioration, I have already talked about it, how we take into consideration this aspect in the models. Well, here the example how that is included in particular model, where you see each of this modification has a reasoning behind it, which follows from how does, in that case, corrosion influence aspects of behavior. How does it change the capacity of the rebars? How does it affect crack formation? How does it affect, in that case, the bond behavior, which is obvious, and also how it develops in time. Now, this one you haven't seen yet, so this is immediately introduction to the program of our session. The model code is structured in parts and in chapters. We start with the basic principles. They are actually the explanations of why we have structures our code like that and what we have been including. And you see the model code covers full stage of relevant for the structures. We start from the assumptions that are relevant for the design, we end up with execution, conservation, and end-of-life treatment, circularity, dismantlement, and we also discuss quality and information management. Very broad, of course. The main focus is on principles of structural design and assessment and implementation of this in practice. And you see, we have 2 chapters that in detail explain the background and the way we have developed safety philosophy meant to be a reference for other code writers. So this explanation is not like give and take. No, it also shows why certain, what is the chain of the logic in defining safety format and defining the principles for verification. Very important part is delay. Well, we have parts on action, but it's just for completeness. So here probably some other codes will be more thorough, but that's impossible not to talk about actions when you talk about design and assessment. A very important part is related to materials and equally important to interfaces. And here, as you see, we will today give you more information about our approach to modeling concrete, modeling non-metallic reinforcement, an innovative type of reinforcement that has potential to deliver strong benefits, and to fiber reinforced concrete. We will also go deeper into ultra high performance concrete, maybe. Yes? Otherwise, Steve is here, you can ask him questions. Yes, let's say like that. Well, chapter that we will not be discussing more into detail, but the very relevant one is about interfaces, concrete and composite material. And here we have included state-of-the-art, if not beyond the state-of-the-art provisions for a bond of embedded steel reinforcement, but also for embedded and externally embodied non-metallic reinforcement. And very interesting part is also on concrete to steel. And I mean, quite often we use this kind of structural solution, so it's good to know it. And anchors in concrete, for practitioners, the important one. Now, the biggest part of the 700 pages of the model code is in design and assessment procedures. And again, you see here the overview of the presentations that you may expect under that umbrella. We cover all types of loading condition. It's static, dynamic, cryogenic, fire, you name it, it should be there. Our aspiration was to allow that provisions to be used in different situations. And there are also quite some progress and innovations there, for instance, with regard to modeling of fatigue and verification of fatigue. Not talking about it today, but just a teaser. Maybe check on the provisions. And then, of course, we go into the different approaches to verification of other pillars of sustainability and how to sustainable decision making in general. Well, here, since we will not be talking about the procedures, we rather decided to show you some examples from practice how the design can prove that it all together works and has the benefits. Execution, a lot of quality of our structures depends on execution, so there is also extensive part of that. And equally important, it looks like one bullet point, but it's definitely not one bullet point, conservation and life cycle management. This is where you find the provisions for conservation, but for quality control, condition control, decision about interventions, execution of interventions, it's all there. Well, forward-looking and definitely relatively thin is the final one on circularity and dismantlement, and that means that we will work on improving that in the future. I skip this one, and I will give floor to the next speaker, hoping that that is just a reminder for many of you, and otherwise please use the break to discuss. Unless there are some questions that you cannot not ask now, but I wouldn't like to take time away from Harald. Yes? So our first speaker, deep dive into concrete, Harald Müller.
Yes, thank you very much for this kind introduction to my presentation, which is on the concrete models in the model code. And I would like to cover the recent advancements we have achieved when developing model code 2020. Well, I'm facing here some kind of squaring a circle, because this stature is nearly 10% of the volume. It's 200, more than 200 equations, a lot of diagrams and tables, and I have 15 minutes to explain it to you. So you can imagine that I can already do a few examples, and perhaps I managed to make you curious to look into more details, and this is one of my parts in my presentation. Well, just looking on the objectives of this chapter is the point, okay, this is to provide the designer with physical sound code type models on material characteristics, first for crude estimates, for more sophisticated method of design, and also for finite element application. Well, this is the only code which should have information to deduce your finite element, like basic consecutive equations. Well, we have kept the level approach, maintaining compressive strength as the main criterion first. This we have to think about in future developments, but for the time being, we could not do it different. Well, as already mentioned by Agnieszka, Model Code 10 was an excellent document, but Model Code 2020 had to be developed in particular as knowledge advances. We have new findings on properties and new kinds of models. We have big changes in the composition of the structural concrete, which is going on continuously. Then we have changes in the requirements for concrete in relation to its application and exposure. And further, it is important today to develop models which allow the inclusion of tests, so performance tests, to improve the approaches. And this I will show you also in a few examples. Just a short overview, the list of subchapters is given here. It's nearly the same as we had for the Model Code 2010, but we, in each subchapter, we had a lot of new approaches. For example, we have new approaches also for multi-axial strengths, new ideas which came in, and also he did a more rigorous distinction between the conventional and the non-conventional concrete. And what is really completely new subchapters, these are the specification approaches for durability specification, and the provisions for concrete material quality control, and the provisions for environmental performance. Those parts are not in Model Code 2010 so far. Well, and if we look now further to the second slide, again here we have the different subchapters, of course, time effect, temperature effects, then the fatigue impact, thermal conditions, transport of liquids and gases, durability is a very important subject, and equivalent performance from non-conventional concrete, concrete recycled aggregates, and assumption for design. Again, I have to state here that we have a lot of really new models. For example, just here shown the new model for temperature effects, and the new model for fatigue. And you can easily imagine if I explain those to you, for each of the new parts, look at me half an hour, it's got to the background and to derive it in a reasonable way. Well, what is really new in the model code is these propose this evaluation of equivalent performance for non-conventional concrete and the recycled concrete models. Well, concrete specification performance-based modeling, as already mentioned by Agnieszka, very important. We have the big challenge that we have considerably increasing environmental requirements. What means we have new types of eco-concrete beyond the provisions of today's standards, and they will enter the market. This is a problem we face, and we want to have a model code which is not outdated in 1 or 2 years. And so, which are the new concretes? I try to summarize it a little bit, and you can subdivide it in 3 classes mainly. This is an ordinary concrete of today. Then we in the future have concrete with high amount of secondary cementitious material. We might have concrete with new cements. I cannot really see new cements in the next 10 years, but there are a lot of research going on. And we will also have the rock powder concrete, which a tremendous reduction of the clinker content and combinations of this. What is the consequence for modeling? The concrete models which are given in the model codes for the time being cannot be easily used for these new kinds of concrete. Please keep in mind, the models we have today are based on our testing experience and research of 50 years and more. And now we have completely sometimes completely new materials, and so we need a way to adapt our models to the new materials. So performance-based modeling is required, and testing is mandatory, of course, and Model Code 2020 gives guidance in this way. I will show you this for a simple example. Everybody is aware what deep it is. I don't explain it. And I show here some shrinkage tests. And here is a model. This is a prediction of the model. And think we have a new concrete, or would you like to know the real behavior of the concrete, then we do tests. And we find the test data like this. This is a model. And then we have to create models that we can adapt the models to our real behavior of the concrete. And this is carried out in the model code. You see here total shrinkage and total creep, the basic formula, and we have here adaptation factors included. And these adaptation factors can be determined from tests. This is described in detail how to run these tests. And they are set, these factors, if you are doing no tests. And the same holds also true for the time development shrinkage, which is also strongly dependent on the kind of concrete which you are using. And though you have here in the time functions for basic and drying creep, also adaptation factors, and also for the time development of creep, the hyperbolic function and logarithmic function, we have included these adaptation factors which you can derive from tests. And the consequence is, for example, your coefficient of variation will permanently be reduced if you run a test with the concrete which is used on bike, for example, from 30% to around about 10%, which is a big step of quality of the prediction. Well, a very simple aspect is the aspect of aging. Next, to consider aging is a characteristic property of the concrete, and we have already in Model Code 2010, only in Model Code 1990, this Arrhenius type function, which describes processes from a physical basis very well. And to adapt it a little bit, we had some dependencies on the compressive strength and the class of cement, and we work with some kind of factor, and you find it here. This factor is included for different kinds of, here it is a factor S there, for the different kinds of the cement. This no longer works with modern concretes. So we have to modify it, and you see the modification for the basic equation is the same, only we did a little bit maybe reference formula, but the difference is in the factor S and S con. And if you compare the both tables in for the explanation, you see that we have here the strength development classes of concrete introduced. We don't look only to the cement, we look to the concrete itself and its composition. And these strength development classes for the normal, rapid, and slowly hardening concretes are structured in a way that they may overly consider further developments. For the time being, nobody really knows how will be the composition of the concrete in 10 years. And so it is structured in a way that it can be easily developed. And I show you as it is for the time being. And you have here again the classes. Here you have the classical kinds of cement with their typical strengths. And you have here definitions for the concrete containing binder compositions, which have a certain amount, and it is easily made, but it is open for more refinement, which can be introduced if it is necessary. It is important that what is given in the modern code is convenient for further development in the future. Well, environmental performance also already mentioned by Agnieszka, and it is clear that we have to give some information for a desire on this particular field. Sustainability, we are mainly talking of CO2 emissions. There are some other effects, but this is the decisive effect. But if talking about sustainability, we have also to keep in mind that service life and performance are also very important parameters. Think about service life. If you have one high emission of CO2, but the service life of the structure is 200 years, then this one high emission is not really a problem. But if the service life is only 5 years and you have a high emission, that is critical. So we have to bring this together. And already a couple of years ago, we came up with the idea of a sustainable potential. We developed a simple formula that sustainability is proportional to performance multiplied by service life and divided by the environmental impact. And now we also try to develop from this a design equation, a basic frame for a design equation for materials and members. And this basic approach is shown in the chapter concretes of the new model code. We defined it using a limit state kind of approach. And you see, for example, here, simplified, we have the global warming potential for optimized concrete, for example, for eco-concrete. Now we have the service life, and we have a reference concrete, maybe a reference of a structure or a concrete or for the year 2020, could be any other. And we have to define a limit state, a predefined limit state as an upper value, and we calculate from this ratio the actual limit state which is given. And this has to be smaller than 1. I show you one example how this really works. This is again this design equation, the basic simple version which can be further optimized, of course. And look to the input. Here we have the eco-concretes to be looked at. You have first to develop your concrete. This is shown here, different kinds of concrete. CO2 emissions are given here, and you have to look for the best one related to CO2 emissions and then use here in the equation. But not only for the concrete itself, but also for the mass of concrete which applied. So as a bending member, for example, and it is shown that you can have the same bearing capacity. If you introduce voids, nothing is new. But we have to apply those things, and you bring both things together to end up with an environmental optimized concrete which goes in here. Well, and then we have to look further to the service life. If we know the composition of the concrete, we can run a completely service life design. We have the formula available in its chapter, and we can calculate how the service life is. Or we can see otherwise versa. You have the service life, and can look which kind of concrete complies with desired service life. And finally, the predefined limit state. Well, this depends what you would like to have. if you go have the situation of 2020 is one. If you want to have in 2040 only 25% of the emission we still have today, then introduce this value. All this value is given by the government or by the... So this is some kind of principle, as you can apply design before it is necessary that the design, the police design person in view of sustainability has two, or let's say simply a common, which it then apply. This is most important. And this is the first simple approach, how this can be developed further. In my country, currently, we have developed a textbook, right, on this, a manual, indicating a lot of cases for different countries and members to prove the validity of this basic approach. Well, durability. Just a short repetition, determination mechanisms, nothing. You are very familiar with it. This has been developed by CEB, one of the mother organizations of the FIB, in the 80s, and was the first time included in Model Code 90. How to come from this basic information to a durability models. And this I will show to you, and which are the approximations which we can offer to the designer. Well, and after a long discussion, couple of years, if we finally ended up with this kind of diagram, and if you have it, it is very simple, but if we don't have it, it's a big program test. And so we said the specifications are, we have three prescribed to make sure that the concrete works within the lifetime. We have a performance type, and we have avoidance of damage by different things, even using another material. This is no longer of interest for me. Prescribed means, prescriptive means concrete composition, and prescriptive rules are given to assure a certain durability. Performance, even more interesting today, the rules which are given are supported by tests, by measurements, with the help of durability indicators. And from a real prediction approach, we have models, physical or empirical models, which are in combination with the performance. And then we have both ways to do. We have maybe a semi-probabilistic, already mentioned by Agnieszka, or a full probabilistic format. And now we define this level of approximation here. We have here this one, it's a simple one, level of approximation 1 is termed in model code, then test by rules, this is level approximation 2, then with semi-probabilistic approach 3, and full probabilistic level of approximation 4. I will show you one example, more is not protocol, that they have imagination how it works. Well, the service life design, we should be done model code for carbonation, for example, based on the LOA4. The basic information is the material properties and the model in the chapter concrete, and the design approach and the design equation with the limit state in the chapter evaluation for CLS for durability. Both are linked and referenced to each other. Well, and this summarizes the design, the input, the analysis, and the result of a service life design. This is input analysis, and this is the result, the decreasing reliability with time. And the input is for material property, the carbonation process. And by this way, you can calculate the service life, which you would like to have for a desired service lifetime, or depending on your particular concrete. Well, now back to the diagram which I have already shown to you, and now it's interesting to know which levels of approximation we can offer to the design. And this I have plotted here, and you can see this is the best we could achieve. It is a full probabilistic design of durability. And you can see we can only have this for carbonation and chlorides, and for thermal cracking and shrinkage. We can do this on the LO4 level. We have nothing with LOA3, but you see very important attacks, sulfate attacks, but also alkali aggregate reaction. We are in a very simple stage. This means there is much room for people and thermal development. And also we have to keep in mind, when I go into details, we consider sulfur only single aspects, only single mechanisms. Most of those mechanisms are interlinked, and they are also dependent on the loading. So if we do a real design, then we have to think about the interrelation and the interreaction with load. Cannot explain in more detail, but it would like just to make, yes, I'm close to the end, to my very best. In my high-speed talk, this is the end. Well, let me briefly summarize. I think this is the further model code, is a further logical and stringent development of model code 2010. The classical strengths-based approaches for modeling concrete behavior is amended by performance-based modeling approaches, which become more and more important in practice. Our distinction is between conventional and non-conventional concrete, and we have a lot of provisions in our equations to cover with new green concretes, where we for a time being do not really know how they behave. But if they come in the market, these are not being that you have to throw your model code away. The equations are made in the form that you can use these formulas also in the future. Well, this is adapted to facilitate, intended to facilitate the adoption of advances. We want not either, as you mentioned it, the development model code must be open for development. So we took corresponding provisions. And what is also I have to mention is we tried, and I presented it already, to be as concise as possible. And some equations need a little bit more background. And this background is given in a bulletin, which is currently under preparation. I hope the first draft will be ready by the end of this year. But it is worthwhile to look into detail. This is the end of my presentation. Thank you very much.
Thank you very much. Steve Foster, we will continue with innovation in concrete, but then we will go into high-performance materials.
All right, so I'm going to just talk about ultra-high-performance concretes today. And I'm going to say, I'm just going to show a few nice pickies. Why steel fibre reinforced concrete? And I'll just go through these. It allows designers and architects some really elegant solutions. So this is the museum in Marseille and of modern civilisations, and you can see the great architectural solutions there as well, very flowable concrete. But I want to put it in the context here of what we don't do well in the model code, and one of the things we don't cover sufficiently well is really ultra-high performance concrete. This will be corrected, right? So one of the things about the new procedures for updating the model code is that we now have a fast way to track new things in. And UHPC, I guess, it's been around for some time now, really important material, but there's only a limited amount of capacity and time that people can do, and it was one of the ones that was probably left till later. So it really comes down to this area of dematerialisation. How do we use it in a sustainable way? And I just go through some of the history, and I'm going to talk pretty much about road bridges today. Of course, the first ones were built in France in 2001. They're documented there. In Australia, New South Wales, we have one that was built in 2005. It was one of the world's first, but it was also the last one that we built, which was unfortunate. There are reasons for that, and I can talk to you in the coffee break why that was. but I was up there recently in Lake Macquarie, and obviously the art is improved over time, although obviously the foundations there are much better because of the graffiti. But if you actually look behind the graffiti, the performance of the structure is performing extremely well. There's no evidence of any cracks or of any durability problems. One of the things we do have to get used to, though, is this. One of the things on some of the bridges I'm going to show you, they actually paint their bridges because of this perception of the fibres that sit on the surface, and you get this nice speckled grey. I think that's, to me, that's a great architectural part of the concrete, right? Speckled brown. But look at the elegance. Many will know, and I've talked on this many times, that the work that my student Yenyi Vu, or Jackie Vu, has been doing in Malaysia. There are over 300 bridges now, and they're expanding into India. They've built the first 2 of 6 plants in India, and as Healy was saying, it's actually absolutely booming through there. I like this one. This is probably not the most economic. I just like it because it just shows the thinness of the webs, the fact that we're using so little materials on this. All right, so just get back to what the model code does cover. It does put in there a model for tension, and that's very important because we need the material properties. We need to have those characterised, and you can't do that with a flexural test. At least we haven't found a way of doing that yet. So you have to do a tension test. Good news is the Americans ASTM, ASTO have a tension test which is being utilised. Essentially, it's defined the same as what we have in the model code. You have a hardening, elastic branch, you have a hardening branch, and then you have a softening branch through that. This value here of the strain, if you like, at that point will vary. In model code talks about 0.1%. The Canadians using 0.2%, and again, so it's what the material can actually achieve on this. The other part, it talks about in very generalistic terms, and we need to, again, improve on these because, instead of applying protection materials, we can use these other systems. So while we identify potentials, and there's a couple of places in the standard that identify, that doesn't really give us really good design rules yet, but it will. And I ask this question deliberately because, we talk about low carbon materials in the cement per cubic metre or cement per tonne or the global warming potential per cubic metre. And we look at, say, how we produce an ultra-high performance concrete. So it's typically around about 800 kilograms of cement. It's got fine aggregates. It may or may not have silica fumes, lots of superplasticizers, and lots of steel fibres. And the question comes is, well, how can that possibly be sustainable? And people come up to me and say, well, we've got to reduce the amount of cement in concrete. And I say, well, no, we've got to reduce the amount of concrete in structures, and we've got to reduce the amount of CO2 emissions. But maybe we need to increase the amount of cement in concrete to achieve that. And this is one example of that. This is a paper, it's in the proceedings, the FIB proceedings. We did some analysis on Jackie's bridges. This is the inventory of data, and you can see here, if we look at the embodied carbon, for example, of the embodied carbon, so 0.478 for UHPC with 1.5% fibres, compared to 0.1 for a normal strength concrete, 0.3, 0.28 for a high strength concrete. So it is actually a very high carbon product per cubic metre of material. Well, let's have a look at this. This is the bridge. They won the ACI award just a week ago for this. It's a 106 metre span. It's a segmental precast construction, which is quite common through Australia, Asia, I think in New Zealand as well. But this was the replacement bridge. This was the conforming design. It was a steel I-girder bridge. and this was the alternative design with the ultra-high performance bridge. As I said, this is the longest span of a segmental precast UHPC bridge to date. And if we look at this particular bridge, those examples, we see even though the bridge itself weighs about 18% more, in the terms of carbon efficiencies, it's less than a half. Right? So we've taken out a solution, a higher carbon solution, and replaced it with a lower carbon one. Let me give you another example which you're less familiar with. This is a fairly recent one. It's one they're building in Singapore. The designers are AECOM, and the consultants, lead consultants are AECOM, and these are the designers, and Jura were the manufacturers of the technologies. Now, this is an interesting one here, and again, we're looking here at full life cycle analysis, not any simplified models, but actually taking out the whole of the structure. Because the problem is with simplified models, when you change a system, design decisions change, right? So the thickness of a slab might change because you've got wider or closer supports to it. So you've got other parts, the piles change because you've got lighter superstructure. So you need to consider the whole of the system. And this is in that paper. It gives you all the details, the full inventory of analysis and the life cycle calculations. But there was another decision on this. So the conforming design was this one here. You'll see it's two spans of approximately 40 metre each. So the alternative design here was a single span of 80 metres. So by doing this, they've actually taken out one pier. Now, that could be a good thing or not, you know, if there's no implements to having a pier in that place. But piers in rivers, for example, we try to avoid, and for other reasons, particularly if they're going over highways where potential for accidents to crash into and the like. So keep this in mind when I show you the figures. We've taken our whole pier, two spans changed to one span. And we do the analysis here, and even with that pier removed, you see a 20% or 10% reduction, so 20% reduction in mass and about a 10% reduction in all the metrics, including global warming potential, 100-year global warming potential. So here's a solution. As I said, it's great to have these simple solutions, but what we're really trying to do is remove carbon from the finished design and product. This one I've shown many times. I won't highlight it. I just like it because it's replacing this 200 thick wall with this 30 to 50 millimetre thick wall. And again, you can just see the emissions changing there. So you're using a lot less material, a lot less transport, a lot less weight, craneages and the like. All right, so I think about 5 minutes left. I just want to go through what standards and guidelines we do have and some order. So the French developed first, the Swiss developed some technical specifications. French came back and developed a full suite for Eurocode, and the Canadians. And I'm going to highlight the Canadians because I think that's probably one of the more advanced codes, very consistent with the way we do things in the model code. And their new standard will come out in 2025. It's due to release January or February next year. In that, we have a whole lot of new models, including for shear. Technical notes and specifications, there are many of those as well. Like this one from Delft, I put this up particularly because it's actually one of the few that actually has a really good study for railway bridges. And the US Department of Transportation has a number of documents, and I'm quite happy for these to be shared later on, if you like, just showing how to use this as different materials and the like. Material standards and guidelines, except ASHTO. This is a really important document because it's actually one of the first standards actually standardises the test for calculating that direct tension. It's really important they do that. to characterise the materials. And there are several other standards as well. Annex U, Annex I now, so Annex U in 2019 for the Canadians, and Annex I also have ways of doing that particular test. The Canadians adopted the ASTO test, but some modifications, which they thought improved it and the like. All right, I won't go through here. I just want to show this, just to emphasise that when we're dealing with these materials, how we place them is really important, right? Because whether it's fibre-reinforced concrete, this is a fibre-reinforced concrete example, or ultra-high-performance concrete, we make certain assumptions about distributions of fibres. And if we do things like, for example, put in form ties across the forms, we can induce weak spots, which can greatly impact the design. So unlike steel reinforced concrete construction, where we have a lot of flexibility in putting place in the steel, we know it's there, we tie it down, we see it. In the fibres, the construction process in itself is very important to make sure we get fibres aligned. All the codes have models for that, and again, just showing some large-scale testing. I won't go through these for time. I will go through this one because one of the other aspects is fire. It's really, really important in these materials, but just to show we can use the same technologies that we do for high-strength concretes. And if I can click on this figure, this is one of Jackie's fire tests. There's some sound with that. It's a big roar, but obviously we're not hooked up to speakers here, showing that you can use micro-synthetic fibres to also control the spalling of ultra-high-performance concrete. So if you have a fire situation, you need to take that into account as well. Agnieszka, I know I've done my 15 minutes, so I think that's probably a good place to stop. Thank you.
Thanks, don't have the leaps on moments in the moment with the CERN ahead of us, yes, because that's like one of the important additional information. While we just completed the work on Monco 2020, we will continue towards its improvement, and this will be delivered in batches, so we don't need to wait for 10 years.
No, that's exactly right.
See select top of the list for including more detailed provision in continuation of what we have already provided for hydrogen.
Absolutely, and in the meantime, you've got the French codes and you've got the Canadian codes to work with. So.
Actually, that's the... That is from...
Well, they're our members.
Yeah, it is, I said. So if there are any questions that will not wait until coffee break, then Steve is here, and he will, of course, be here also in the second part.
Yeah. Talk about shit. All right.
You have more time. Yes?
Thank you.
And now, from concrete, we will move to innovative reinforcement, because that's also quite often a solution that is being used for different reasons. One is the weight, another one is reactivity, you can name it, and also quite often in combination of steel reinforced, steel fiber reinforced concrete. So Georgie Balance will share with you the up-to-date information about the MOPOC and its contact from that sphere. Please.
Thank you.
Agnieszka. Ladies and gentlemen, this is one of the most exciting, enjoyable part of the model code, and I'm happy to report about that. We have activity in FIB and also in ACI since the beginning of 90s. We had running groups, at least one, and combining many members. This was the first group, including more than 100 members in the House group, which was the largest House group. Yes. I would like to acknowledge my colleagues as well. Sándor Solyom is sitting here. We are working in the same field. This is a large field and a lot of future work. I'm happy to remember to our visit together with Steve Mattis, Maurizio Guadagnini, and there was there was another colleague, to an FRP strengthening workshop. This part was part of presented in Christchurch, then in Wellington and in Auckland, and organized by Alessandro Palermo. We were very glad to have it, and it was we were very tired afterwards because we arrived here, a lot of traveling, also in the New Zealand as well in the country, and returned to Europe. Yes, you can see here the program and some photos from Christchurch, from Wellington, and the Auckland meeting. So we enjoyed very much, and this was a special organization that because Alessandro Palermo offered us local colleagues as well. In every case, we were extended, our contributions were extended with local colleagues and local experiences. We enjoyed very much, and it was very important FRP. The obvious reason to use FRP is to avoid or to reduce durability because the electrolytic corrosion is excluded, but there are other advantages and sometimes disadvantages as well too, which we shall see soon. This is one element which we pre-stressed with FRP, all the tensile reinforcement, the bottom left, you can see, and also in the bottom right, it was FRP, 2 carbon fiber pre-stressing wire of 7-wire strand. You can see that it was just after 1 month in the outside exposure, the top reinforcement was still 7-wire strand, and that is already corroded, and the bottom reinforcement, there was no sign of corrosion as well, at all. You know very well that there are plenty of FRPs, different fibers and different matrices. I do not want to show all of them. The highest level, the most important application of FRP is for pre-stressing because the stress of fibers are rather high. We reach 3,000, 4,000 newtons per square millimeter with the fibers. So the most important, most promising applications are in pre-stressing. You can see, so first I would like to explain some technological aspects and modeling aspects and some future work as well. You can see on the top right diagram, top right photo, steel, aramid, and different compositions of carbon fiber pre-stressing strands. Let's take some important material characteristics first. We know that the fibers have high strength, but the deformation is limited. You can see here that the ultimate strain is about in the range of 1 to 2, maximum 3%, so below 5%, which is normally required for steel pre-stressing, for example. And the strength levels are given here. You can see that there are different solutions. Very important is the second parameter. I have to go into details, which is indicated by FF100 euros. There was a very long discussion, and we are very happy that the industry also supported the solution that when we apply the strength value in design, we have to apply the long-term value of the strength and not the starting value of the strength. And there are differences, there are considerable differences of these values. So there are many tests, and we also running these tests as well, especially for some, of course, different results using carbon fibers or glass fibers or aramid fibers. So very important, and we are going into this direction that in design the long-term value of FRP will be used. This is mentioned also, as you can see here. And we can see differences for carbon fiber, CFRP, that is about 90% after 100 years. And there are different values for GFRP, AFRP, and basalt fibers, BFRP, so somewhat lower than for carbon. Modulus of elasticity is well known, that we can decide by the production the level of the modulus of elasticity. If you want to increase the modulus of elasticity, the ultimate strain will decrease. So you have to analyze, and the price is increasing also if the modulus of elasticity increases. So we have the chance with carbon fibers to have higher moduli of elasticity than that of steel, but normally the other fibers can provide lower values. You can see here about 50,000, 70,000 Newton per square millimeter. So that means automatically that the deflections will be higher. Yes. Creep rupture is the word. The tests for 100 years strengths are practically creep rupture tests, and I mentioned in the literature. During the production, you have to decide how to prepare, how to finalize your FRP reinforcement. You can see the photo of the differences to steel. So the FRP reinforcement has completely different bond and surface properties, which we should consider. So normally, the end layer of FRP is produced additionally, and the problem is that even under relatively small slip, it can split from the surface. Not in all cases. If you use sandblasting on the surface of the FRP reinforcement, you can have even two bonds, too high activity of bond, and too concentrated force transfer. So there are very different solutions for bond and consideration of bond. But you can see, and it is also codified in the model code, that the bond-slip relationship is different for steel and for bond. That is a very important aspect. You can see some values from one of the CFRP pre-stressing strands if you want to use it. The technological aspect is very important because you cannot just catch the pre-stressing strand if it is an FRP and try to apply force in the pre-stressing element because you can destroy the FRP. So there are special ideas, special solutions, special finalization. How can you do that? We normally speak about pre-stressing level of 50, 60%, sometimes 70%, but even in this case, there is a very high concentration of stresses. So anyway, this is one solution which works. We tried, so it is safe to use, safe for the workers and safe for the design as well. So you can apply the level that you want to design, to apply in design. In this case, you have a CFRP strand to the left. You have a special anchorage head with a multi-layer of elements to anchor it, and you apply your pre-stressing force due to a steel pre-stressing element in a coupling device. It works actually without any problem. This is one of the best that we have found in the market. There are special problems which you should not forget about that. The FRP is very sensitive. For example, this is a typical problem, so it could be a typical problem. So if the opening for the pre-stressing strand, which is FRP, this is CFRP of course, at the end of the element, and the left-hand side there will be casting of the concrete. In this case, you can cut the top fibers at the extreme, the perimeter. So this is a real problem that you can produce difficulties if you don't take care enough. So the processing strength of FRP must be able to run and without any problem in longitudinal direction. So this is just a practical question. So this is an element we also produced and tried, so you can produce really pre-stressed elements. There are two pre-stressing trends here at the bottom. This is the load deflection diagram. Of course, bilinear, and you can see a very high, we were even surprised, of course, this failed in tension. This was designed to fail in tension, but after a very long reflection. Fatigue is one of the most important area or characteristics, because at least in Europe, GFRP in Germany, for example, I don't know exactly all the countries, but there is some more questions than answers at the moment, but I'm very happy to see here values as well in Model Code 2020 for fatigue. So there was a kind of different use for different fibers. So the processing level related to the fibers, and there are different values, maximum values of the fatigue load, 60% for steel, and also 60% for carbon fibers, but a little bit lower, but not much lower, 50% for glass with epoxy. However, this is very important, the last column, what is the maximum fatigue stress interval? For processing stress, we know everybody. Normally, we use 200 Newton per square millimeter, and this is a very positive answer here, that we have much higher value, 350 and 310 for carbon fibers. This is very positive. And then we can see the last value here, glass and epoxy is somewhat lower, but not zero. You were able to see previous tables that there was no value there. So we are happy to have that some value also for glass epoxy as fatigue strength, and I was very happy to listen to a young lady to dealing with this question. Relaxation is not so problematic. So as I mentioned, that this is a kind of summary of this. We should not go again in details. That the anchorage problems have to be solved before the application, and the long-term strength is important. The safety factor was already a very long discussion, and you were able to find different safety factors from that value which is given in Model Code 2020 for every, which is a good approach and easy to apply. So we now, after long discussion, we agreed to have safety factor, material safety factor 1.3 for all kinds of fibers and matrices as well. So this is very important to allow the application, not to stop, not to delay the application of FRP. We have already quite many applications in bridges as well, and different constructions, and therefore we were able to establish this value, and you can rely on this value, and we may decrease it for carbon fibers for the future, because that was a question many times. We know that, and this is very important, if we speak about design philosophy, that we have to see concrete failure and not FRP failure, since FRP is linear, elastic, and brittle. So the failure philosophy in the Model Code 2020 is to have to avoid failure of FRP and to have concrete failure, and this is the way that we can regulate it. There are further aspects which we could discuss. The important is, for example, for the shear reinforcement is normally banded or bent. This word is not quite good for those who learned English. So we are not speaking about bending like steel bars. You make bending after the production of steel, but in case of bending and the stirrups is bent, is produced before hardening the matrix of FRP. So you produce the form of the reinforcement or longitudinal reinforcement, if you want, or the stirrup before hardening of the matrix, and you realize a problem that is often mentioned, that there is a reduction of owing to the bending, or owing to this type of bending. If you go into details, the proposal in many papers and literature and codes as well, to apply 0.7, about 0.7 reduction for any bend, even any stirrups. This you can use, and you can live with that, but there we can go into some details briefly. So it is very important, so not to avoid, not to forget about that. Yes, okay. This is what I wanted to mention. There are several solutions. The best one is this by Sherp, because there is no deformation on the surface, but there is indentation of the surface, which allows a quite active bending. Their syrups are the best syrups, according to our opinion. So the reduction is smaller, so you can apply instead of 0.7 a higher value. But not in all cases is the situation. So this is a big question, big problem for the industry itself. How can they solve it? How can we live with that? So there are. This is a very good diagram on the left. You can see that the length of the fiber or the fibers itself, fibers themselves, will be different. And this is the problem actually. And the syrup look very ugly. If you see the syrup before hardening of the matrix, owing to the differences of the length of the fibers in the bent corner. So this is a real problem. Many companies are working on that, and also we are working on that. We are trying to. This is one of the developments by us, and we hope to arrive at a much higher value. You can see that the fibers here
are hard and no lady of what the face of the formation of the
fibers in the smaller radius. I don't speak about strengthening. But strengthening was very successful from the beginning of 90s. There were some strengthenings even of, at the end of 80s by applying FRP. There is the external bonding, and there is the near surface mounting technology. There are many advantages. I don't go into details. I would like to open your eyes with the last two slides, which is not discussed in Model Code 2020, but discussed by many colleagues who are working in 3D printing of concrete. So how can we use efficiently the FRP in 3D printed concrete elements. And this is one of our proposals. We did this in our laboratory. The idea is, so we should further develop, so you can print easily sections of bridge girders. So this is 1 meter depth, 1 meter deep, this element. And you can apply in a later phase, depending on the length of the element, and depending on the load of the whole element, and depending on the design, additionally afterwards FRP in the bottom flange, pre-stressed or unprestressed. So this is a concept which is not completely developed, but is a new concept. But with FRP is the best one. And my last photo is also from our laboratory to apply FRP in elements which are printed in 3D printing. So in 3D printing, there are a lot of possibilities, and FRP gives normally the best solution. So I have a lot of, I don't know how much time we have, no time. So I don't read my conclusions. I have seen it already, the face of Agnieszka. So there are a lot of advantages, but you have to be careful. That is very important. Thank you very much.
This presentation concludes the first part of our series of presentations.